You will remember that with a t-test and with a chi-squared test, we had certain assumptions that we had to meet. This is definitely the drawback to linear methods. They usually have a lot of assumptions, and if your data doesn't meet those assumptions, your result will be biased. In some cases, you can adjust your statistical tests to deal with them. In some cases, you cannot. So for the most part, we usually can. So there are four main assumptions to an ANOVA. So your observations, so one corn would one row of corn or corn plant, it would be the best way to put it, would need to be independent from the other corn plant. So this doesn't mean that weather affects both of them. It's basically, say if one corn plant dies, automatically the second one dies. That would mean it was not independent. However, if one corn plant dies, is really not going to affect the actual next one, independent of like the weather and things that actually would affect it. That's not what I mean. Those would be the things that you would actually test in a significance test. So basically, the outcome of one cannot directly impact the outcome of another one. So there's no way to really test this, but your domain knowledge, you should have a good idea whether this is met or not. But it's something to keep in mind. So the next thing that we're going to look at are our residuals for our next assumptions. So remember, the residuals are our value in our data set minus the mean. So we've seen a QQ plot before, so I'm going to show that. We looked at that when we looked at t-tests. So that will be, I went over that in more detail, so you can go back to the videos if you need a review. So in this case, the residuals have to be normally distributed. And I will show a little bit more about what that means in a second. So this would, first, I'm going to go over checking for outliers. So this helps you look at normal distribution as well as outliers, this here. I'll show you the code in just a second. So here, you can see our residuals. So our values minus the mean are on our y-axis, and our fitted values are down here. So we're going to go over more about how you would use a model to calculate predictions when we go over regression. So you can think of this as a predicted value that goes through the ANOVA model. And we have our different groups here. So these are our fitted values or our predictions. So this would basically be the mean of the short, the mean of the middle, and the mean of the long. So in practice, that's what it would actually mean. So we have our error value over here, our residuals. So we are seeing 3 of them are labeled with numbers. These are outliers by definition. However, when I'm looking at this, 77 would be a judgment call, but they seem to be pretty close to the rest of my group. So I'm not going to remove them in this case. We can get a good idea of whether they should be removed from another test that I'm going to go over in a second. So you would want to be aware that there are outliers here and look at your further tests to see if they're violated. And if they are, you can come back to those outliers and remove them. In this case, by a gut call from doing this for a long time, these will be okay. So we see those outliers. Also, if you see a very specific pattern within our residuals, say we have a whole bunch of lines way up here and then just a very few down here, for instance, that would mean our data likely isn't normally distributed. So you would want to do the next test and see, but you would want to be suspicious if you saw that here. So they're not extreme outliers. There are outliers, but I'm going to keep an eye on that and keep that in mind, but I'm going to move on. So we said normally distributed. That is also our residuals being normally distributed. That is a requirement for this test as well. So residuals, actual value minus group mean. So what we would do is something called a Shapiro-Wilk test. I believe we actually went over this before. So if we're running that Shapiro-Wilk normality test, we're running that here. And this is the code we would do to run it. So first, we basically have to pull our residuals from our model. So this extracts the residuals from our ANOVA model and assigns it to these values. The next thing that we're doing is putting those residuals into the Shapiro-Wilk test, which is Shapiro.test. It will then print this result. So our p-value here is above 0.05, which means that we can assume that our residuals are normally distributed, and we can move on. I would like to show one thing just for reference. Just remember I said that if you have extreme outliers, your this test might actually indicate whether there is a problem or not. Remember we got rid of that really, really, really high outlier? I'm going to not get rid of that and show you how that changes these results. I'm going to rerun real quickly our Shapiro-Wilk test. All right. Going down to Shapiro-Wilk here. We're going to take those residuals. You'll see here that our p-value is basically 0. That's what it's showing here. So that 1 point all the way up here changed our p-value from 0.15 basically to basically 0. So we saw those outliers before, but we didn't get a non-significant result with particularly when we scroll up. When we had this point removed, we were pretty clearly within the range of normality. However, when we didn't remove this, it totally changed. So if you're trying to decide or make a judgment whether an outlier is too influential, this, say you guess not, if this is showing to be significant, then you would probably want to go back and remove those outliers, just like we did here. So let's go back and redo without that outlier, because this is one we definitely do not want in our data. So here we're seeing the Shapiro-Wilk test and what is outputted there. Are there any questions about Shapiro-Wilk? Chat is also okay since I'm not in full screen. Okay, the next one, we're going to test the normal distribution. You can usually test something numerically and you can test it graphically. We saw this for the t-test, our QQ plot. So standardized residuals, those would be very similar, like when you see a bell curve. Remember our z-score was a standardized value. So basically no matter what, so whether it's bushels per acre or inches, something very big or very small, they're all going to be standardized and they will fit on an axis that looks like this. So that is, remember what standardized means. So down here are basically the our quantiles of our data points. So it would be these quantiles. So it would be for the third quartile, for instance, is 75%. So it's looking at those percentiles or something very similar. But basically, you want to see if this follows an approximate straight line. If you see something that looks pretty straight, like we're seeing here, that means your data is normally distributed. If you see something that looks like an S, like that, that means you're in trouble. If you see something that is like this, that means it's not normally distributed. So any pattern that is not a straight line is a problem. You actually have to run a different type of test. I'm not going to go over it today, but if you Google it, it's just if you change certain arguments, you can make corrections for that, or you can transform your data. Just Google it, and it'll give you a lot of ways to deal with that. So with our numeric test and with our graphical test, we're seeing that our data both ways looks normally distributed. So we're good on that area. The next assumption is homogeneity of variance. So homogeneous variances. So in this case, we want to look if our variances between our groups are significantly different from one another. That's a problem for this ANOVA. They have to be similar. So you can go back and look at the formula for variance. I believe it was one of the first slides. So if the variances are significantly different from one another, we cannot run this test, or we have to run it with a correction on it. Usually it penalizes the error value, and it changes and it makes it harder to achieve statistical significance. Again, Google that. I'm not going to go over it today. There's too much. So our variances between levels they cannot be statistically significantly different. In order to test this, we use the Levene's test. Levene's test looks at homogeneity of variances. So if our p-value is below 0.05, that's a problem. That means that our variances are not equal to one another significantly. So in this case, we're getting a p-value of 0.56, which then means that our variances are equal significantly. They are not significantly different from one another. We can think of them as equal and assume that that's okay and move on. So that, in addition to outliers, those are our assumptions. So I'm going to finish going through in the actual code. So we are seeing with that Levene's test, we're seeing that result. It's not significant. So what that tells you, so we basically put a check mark next to no significant outliers or extreme outliers. Homogeneity of variances, we're good there. Our residuals are normally distributed, and our data values are independent from one another. If you put the checkbox next to all of those different assumptions, that means in reality, when we go up here, these results are valid. Now, after we've tested all that, we are confident that these results from our ANOVA are correct or very close to correct. So we can trust this p-value here. We can trust these differences. We can trust our results. So that is what running the assumptions after we do our model tells us. So if you remember, I said when we do this, we cannot see how those different levels are different. Remember, just to recap, we would have to run the Tukey's HSD to see that. So now we can be confident in these as well.